Hello, I am Mukul and I'm taking part in the Breakthrough Junior Challenge, and my primary area of study is mathematics. In this video, I will talk about inverse functions. Before we move on, let us understand what a function is. Let us consider two non-empty sets A and B. A function relates these two sets. It takes an input, that is, an element of set A, processes the input and gives the output as an element of set B. The function maps elements from A to B and is denoted as f from A to B. Since all elements of set A and B are real numbers, the function f from A to B is real valued. The set A is known as the function's domain, while the set B is known as its codomain. There are many different types of functions. Let us take into consideration two of them. Since every element of set B is linked to some element of set A, the function f is onto. Also, every element of set B is linked to only one element of set A. Hence, f is a 1-1 as well as onto function. Functions which are both 1-1 and onto, such as f, are known as bijections. Assume that we want to map an element of B back to its corresponding element of A. In such a situation, we use the F inverse function. For every bijection F from A to B, there exists a unique mapping from B to A denoted by F inverse from B to A. The function f raised to the power -1 is known as the inverse of f. Let us learn more on inverse functions. Since f mapped elements from A to B, its inverse will map elements from B to A. Hence, the domain of f inverse is the same as the range of f, while the range of f inverse is the same as the domain of f. In simpler words, the inverse of a function can be understood as follows. You give an input x to a function, which in turn gives you an output y. The function which gives an output x when given an input of y is known as the inverse of the function. Let us understand this with an example. Example: if a function f of x gives the birth year of a child chosen from A to E, then the function which gives the name of the child when its birth year is given is known as f inverse of x. For example, if child A was born in 2000, f of A will give us 2000. We want to map 2000 back to child A. Hence, we write f inverse of 2000 is equal to A. Let us see an example. These are the steps we need to follow when inverting a function. Write the function. In our case, the function is y is equal to 2x plus 1. Solve the function for x to get x is equal to y minus 1 whole divided by 2. Since we are inverting the function, we swap the variables. After swapping, we get y is equal to x minus 1 whole divided by 2. This is written as f inverse is equal to x minus 1 whole divided by 2. Let's plot this function graphically. In the previous example, we swapped the x and y variables while we were inverting the function. We do this because to invert a function, we must find a line such that every point on it has the y coordinate equal to its x coordinate. Such a line is the y is equal to x. Every function is a reflection of its inverse in the line y is equal to x. In the previous example, the original function y is equal to 2x plus 1 is represented by the blue line. The red function represents the inverse of original function, that is y is equal to x minus 1 whole divided by 2. So the red line is a reflection of the blue line over the y equal to x, that is the green line. Let us now move over to trigonometric functions, which include sine theta, cos theta, tan theta, and more. As we know, for a function to be invertible, it needs to be 1, 1 and on 2. But the trigonometric functions are not 1, 1 in their original domains. More than one value of theta gives us the same value for sine theta as shown in the example. Sine 30 degrees is equal to 0.5. But sine 0 but 0.5 is also equal to sine 150 degrees. Hence, this proves that trigonometric functions are not 1-1 functions. To convert trigonometric functions into 1-1 functions, we must find the smallest interval of theta for which the range of a trigonometric function, for example sine theta, is -1 to 1 inclusive. Such an interval, which includes all the values of the range of the function, is known as the principal domain of the trigonometric function. Let us try to find out the principal domain of sine theta. It is also important to understand that there may exist more than one principal domain for a given function. We draw a unit circle and search for points where the sine theta function extends from sine theta equal to 1 to sine theta equal to -1. One such interval is from pi by 2 to -pi by 2. Therefore, we can say that all values of sine theta are covered in the interval -pi by 2 to pi by 2 inclusive. The table shown gives the principal domains and ranges of the trigonometric functions. In these domains and ranges, the trigonometric functions are invertible and are hence bijectives. Let us elaborate our concept of inverse functions to the trigonometric sine function. If we are given an angle, we can find the sine of an angle. But if we are given a number x and asked to find the angle whose sine is x, then we get stuck at that point. In such situations, we use the sine inverse or arcsine function. If sine theta is equal to x, then theta is equal to sine inverse x. If we give the sine function an input, it returns a value. If that value is to be found out, it is substituted in the sine inverse function. Hence, sine and sine inverse are inverses of each other. Let us do an example. Sine 30 degrees is equal to 0.5. Hence, 30 degrees is equal to sine inverse of 0.5. The same concept can be extended to all the trigonometric functions. All trigonometric functions are invertible. The values for which they are invertible are given in the table on the screen. With this, I would like to end. Thank you.